We're doing proofs involving ideas of similarity. In general, proofs are extremely important in maths. They give maths its power because you're able to generalize. You're not just showing something in one case, you're showing it for all cases, which gives it tremendous power and credibility, unlike any other area of study. Most things are based on arguments and evidence, but proofs are conclusive, they're proven. It's important when we do proofs, even these fairly straightforward ones in similarity, that you set the work out properly. They are formal, they're set out strictly. They're not very long, not these ones at least, but it's very important that we don't cut corners. We must set them out formally, properly. We'll be proving triangles are similar in this video. To prove that triangles are similar, we list any pairs of corresponding equal angles and pairs of sides in a given ratio, which should sound familiar because these are what all of our tests are based on. So the three main steps are here in red, blue and green. You give reasons at each step. You write a similarity statement. There's two examples there. Remember, there are two possible symbols for similarity we've seen in past videos. And third in green, we write the triangle test, the similarity test, and we know from our previous work there's SSS, SAS, AAA and RHS. If you've forgotten those, you may need to rewatch some of the old videos or see me. We have two examples here. Prove that each pair of triangles is similar. Let's look at this first example. We can see the two triangles. We have to prove that they're similar. So we start with our three steps. Firstly, we see that angle BAC is equal to angle DEC. Because we have alternate angles, that's the Z rule. Sometimes the Z rule can be turned on its side to make an N rule. That means if you've got two parallel lines and you have a transversal connecting them, these two lines that are parallel cut by the transversal will make two equal angles. You can see the two angles I'm talking about there, or in this case that'd be there. That's alternate angles, and we write the reasoning on that step there. The other reason why that step is true is that DE is parallel to AB. So you need that to show that alternate angles are there. So you can see that little symbol, plus looking at it visually, you can see that DE and AB are parallel. And remember, that's our symbol there for parallel. Next, angle ABC is equal to angle EDC. Because they're alternate angles. Remember, a transversal cuts and connects two parallel lines. The two parallel lines again are DE and AB. So you can see them here in red. The third reason is angle ACB equals angle ECD, because vertically opposite angles are equal. They're vertically opposite. So you can see in green there, they're vertically opposite. When we have two straight lines intersect, like we've seen previously, we have vertically opposite angles. So we have our three reasons, and we come up with a statement at the end. We can say in conclusion, the concluding statement is important. Therefore, triangle ABC is similar to triangle EDC because of the three reasons, and that three reasons makes up AAA, three angles, and that's the end of the proof. The second proof, this one is different. We can see firstly that the ratio of AC, which is the bottom line here, over DC, which is there, is 18 on 6, which equals 3. Now it might be a bit hard to see at first that they are corresponding sides. You may need to pause the video to see that. It is not obvious at first. Then we have angle ACE and angle DCB. Pause the video if you need to. Those are a common angle. Both triangles use that angle. It's down here in green. Lastly, we have EC over BC, which is 12 over 4, which is the same ratio as above. So we have corresponding sides in the same ratio. So what we have there is enough to prove that they are similar. We can say, therefore, triangle ACE is similar to triangle DCB because of side, angle, side. Remember, the A here means an included angle, and because it's common, it's included.